No, you good, you good. Oh, sorry. Yeah, yeah.
Okay, I think we have everybody, so we'll get started. Give me 1 second, I just want to put this up. Okay, great. I think we have everybody here. Thanks everyone for joining. For Insung's, it is going through, right?
Mm-hmm.
People online here. Okay. What's this one?
This one doesn't have.
Okay. Okay. Great. Okay. Good. It's just the advanced setup here. Okay. Thanks everybody for joining for Insung's dissertation defense. I guess a bit of logistics first. So we'll have this session be roughly 45 minutes presentation, and then 15 minutes for sort of open questions from the audience. Please, try to formulate some good questions for Insung. Then at that point, we'll ask everybody here to leave, and the committee will have a closed door session for an hour with Insung. I think we have the volume situation figured out where we can ask questions in the audience and everybody on the Blue Jeans should be able to hear it. But if you're on Blue Jeans and you cannot hear a question, please indicate it in chat and I'll tell Insung to repeat it before he answers, okay? All right, with that, I'd like to introduce Insung. So he's been with the Epic Lab for the last 5 years now, almost exactly on the 5-year mark right now. And when he joined the lab, we were just getting started. So he was one of the very first cohorts of PhD students. And he came in and worked by himself on our hip exoskeleton project, first kind of primarily working in mechanical design. He did what I think is quite impressive, and anybody who's done robotics knows that it's really difficult to build your own hardware. And he's built his own set of hardware 3 times, so 3 iterations of hip exoskeletons, with each one being a major advance that we're really proud of. And I think he'll detail some of that in his presentation. Some of the things that you might not hear is early on he helped put together an RO3 that we got funded to do a lot of the stroke work, which you'll see much later in his presentation. That's very exciting. And another, I think, highlight is when we sent Insung to the IEEE I-Core conference. He had some discussions with Samsung, which went really well and actually really helped our lab create a new collaboration and funded project through Samsung that we're pretty excited by, and that was really completely because of Insung and his networking capabilities, which I think is really awesome for a PhD student. One other thing that I'd like to highlight is his ability to mentor people. I think a lot of people in the audience know this, but even recently he got an award from GTMI for being a top undergraduate mentor. And he's mentored a lot of undergrads to date, and he's also mentored a lot of our grad students, and that's really shown out. And that also is shown in his publications. He's got a lot of undergrads and mentee grad students on his publications. And he's also been a part of a lot of other grad student publications, which is really cool. Almost a 50-50 split between first author and co-authored papers, which I think is really shows his ability. One of the highlights I think in the Epic Lab for Insung has been his ability to be a team player and work with a lot of other students on these projects. And with that, I'll hand it over to Insung on his dissertation, which I think will be really exciting today. All right, thanks, Insung.
All right, thanks so much, Aaron, for a nice, warm introduction. Hello everyone, my name is Inseung Kang, and I'm a PhD candidate in mechanical engineering at Georgia Tech. And today I'll be presenting my thesis work on the adaptive user state estimation for assisting human locomotion using powered exoskeletons. But first, I want to give a little bit of introduction about exoskeleton technology. So over the years, there has been a great advancement in the field of wearable robotics, and these exoskeletons can typically be used for 3 main applications. The first is human augmentation, where we can utilize exoskeletons to enhance physical capabilities of able-bodied humans, carrying heavy objects or maybe marching for long distances. And then we can use exoskeletons as an assisted device, where we can provide partial assistance to both able-bodied and clinical populations, improving the overall community ambulatory capabilities. And lastly, we can utilize this in rehabilitation effect, where we can alternate the overall physical attributes for long-term benefit of a clinical population. Typically, these exoskeletons that were developed in the past were often bulky and big and really didn't work. This was mainly because the field failed to realize the overall human-robot interaction aspect when using an exoskeleton system. So the field started to really develop more of a single joint targeted exoskeletons. Researchers such as Mooney et al. Or Collins et al. Start investigating developing ankle exoskeletons because the ankle joint provides large mechanical power during locomotion. Recent literature study by Sawicki et al. Has indicated that maybe hip joint is also a targeting joint that can be beneficial. This is mainly because hip joint is inefficient, unlike the ankle joint, because of the overall muscle tendon structure requiring additional muscle work to generate similar mechanical power. So recently, there has been a lot of research in industry groups such as Ding et al., Giovacchini et al., or Honda Exoskeleton that were able to develop hard hip exoskeletons that have shown promising results. I want to bring in a little bit better context in terms of energetics. So we're seeing on y-axis net metabolic cost benefit of using an exoskeleton system. So more negative number is actually better. So if you can see, over the last decade, we've gotten far better at developing exoskeleton systems by further reducing the user's metabolic cost. But if you look at closely in the recent 5 years, the greater metabolic cost benefit came from assisting the hip joint. So there's definitely a benefit of developing a hip exoskeleton system. So as the field got better at developing exoskeleton hardwares, researchers started to investigate how do we control these systems. So researchers focus on optimizing the system levels to develop better controllers. Studies such as Collins et al. Or Young et al. Start investigating optimizing a system magnitude or timing and have shown that there is indeed an optimality in assistance, that more assistance is not necessarily better. And recently, leveraging these domain knowledges, researchers such as Zhang et al. Started to develop more advanced controllers, such as automating the overall system to tune on a user-specific basis. So then the question comes down to, how do we actually translate this technology into the real world? One of the key limitations of current literature studies is that often these studies are conducted at a very static, constrained environment, such as laboratory setting. In daily activities, a person not just walk on level ground locomotion, but actually experience dynamic movements such as going up the stair or coming down the ramp. An exoskeleton should be adaptive to comprehend different environmental and user state information during these movements. And during dynamic locomotion, exoskeletons should modulate relevant control parameters to maintain the overall optimal system level. I can illustrate these aspects in a more of a general pipeline. And then we can draw an exoskeleton translational pathway. So on the far left, you can see that there's a laboratory setting where we're understanding the fundamental science of what an optimal system is. On the far right, we're seeing a person wearing an exoskeleton system outdoor in the real world. And there's a clear gap and need in between the two where we need to bridge those two aspects. And this is exactly where my overall thesis work revolves around. With that, I've developed my central hypothesis that overarches my entire thesis work. That an adaptive approach of accommodating user state information and modulate exoskeleton system accordingly during dynamic locomotion will improve overall human exoskeleton performance. My central hypothesis has 3 main research aims. Aim 1, exploring the optimal hip exo design to approach for maximizing human exoskeleton performance during wide locomotor tasks. Aim 2, understanding how to better estimate user state variables and improving the hip exoskeleton control over a stimulated community training. And last aim is quantifying the biomechanical effect of using these exoskeletons in improving gait functions of a stroke patient. So recapping my 3 main research aims, aim 1 is optimizing hip exo design, second aim is user state estimation, and aim 3 is translating to clinical population. But first, I want to talk about how do we optimize hip exoskeleton design. As you can see, there are a number of different hip exoskeleton designs that have been shown in the field. And most of these devices have shown promising results. But one of the limitations of these designs is that most of these design studies are often developed with researchers' design principles. So there's a lot of personal preference that's going on when you're developing this system. And there's not much of clear information about why certain actuator was used or why certain orthotic interface was selected in developing these hardwares. And this is a huge limitation because it is really hard to understand what is an effective exoskeleton design. And as I was moving into grad school and developing these hardwares, I really wanted to bring up a more of a holistic design guidelines for developing an effective exoskeleton system. I want to talk about how do you design a part-of exoskeleton. There are multiple key design criteria, and the first is the overall device needs to provide hip flexion and extension assistance in the sagittal plane. And I want to focus on developing a system that is fully autonomous, potentially to be used outdoors. And the device needs to fit and accommodate wide ranges of body sizes, potentially to be used in a clinical population. And lastly, the device needs to house different onboard sensors, potentially to be used for user state estimation. These exoskeletons can be controlled with a 3-tier control approach, where each layer serves a specific purpose. On a high-level layer, we can integrate a user state estimator, such as intent recognition, or maybe estimating either user's walking speed or ground slope inclines. These state variables trickle down into mid-level layer, where we can implement a dynamic equation that can generate the overall joint torque trajectory. And these dynamic equations can be a conventional control approach that has been shown in the field, such as torque control or impedance control. And finally, this torque command goes down to the low-level layer, where we can realize the actual joint torque that's being outputted from the actuator through a conventional closed-loop feedback control, such as PID control. To understand a better exoskeleton design, I've done a number of initial pilot work to better design my system. The first initial pilot work was understanding the effect of a system level. So this study focused on understanding the relationship between the exo-assisted magnitude and the user's metabolic cost. And the increase of assisted did not necessarily yield better metabolic costs, but there was rather a U-shaped trend. And this was because higher assisted induced a change in the user's kinematic patterns, leading to a marching gait, which is very inefficient in terms of user's metabolic cost. And our results indicated there's a theoretical maximum of about 6% reduction compared to the baseline when the assistant is optimized, indicating that there is indeed an optimal assistance. And this was well in line with other literature studies. And this information led me to better understand and fine-tune the required design specification for the next generation actuator development. Another initial pilot work that I've investigated was understanding the effect of user interface. So often, exoskeleton designers utilize an off-the-shelf interface, which overall leads to poor performance because there's a lot of compensatory movement that's happening around the torso area. And as a proof of concept, we developed a custom user interface that has a better anchoring mechanism as well as mechanical leverage. And using this system, we did the exact same initial pilot work as my first work, and our custom interface was able to further reduce the user's metabolic cost across all conditions, up to about 9% in the maximum metabolic cost difference. So this results kind of at least indicate a direction that developing an exoskeleton system is not just about developing a novel actuator, but also figuring out an optimized user interface. With these number of initial pilot works, there has been a number of iterations of my hip exoskeleton design throughout my course of PhD work, where my hip exoskeleton version 1 focused on providing nominal assistance during level ground walking. One of the key limitations of this device was that it wasn't able to accommodate average walking speed. It was rather just slow. So knowing the result from my first initial pilot work, I lowered the overall assisted capability, but increased the overall walking speed, leading to version 2 exoskeleton. And using this device, I was able to accommodate nominal walking speed range. But this device still had limitations where it wasn't able to accommodate different locomotion modes such as ramp or stairs. That led to my final version of hip exoskeleton version 3, where I can now provide assistance in wide locomotor tasks and wide speed ranges. One of the key aspects of designing an exoskeleton system is developing a robust actuator. We utilize the concept of series elastic actuator, where we can integrate an elasticity in series with the actuator output. And using a simple Hooke's law, we can measure the output joint torque, allowing us for a closed-loop torque control. And we try to select the best components for this actuator to maximize the overall performance by searching the power-to-weight ratio, because weight is a critical factor in regards to human performance. Design criteria such as joint torque or angular velocity were based off of human biomechanics during multimodal locomotion. With this, we selected harmonic drive gear train as well as high torque density drum motor. And our final actuator design was able to handle dynamic movement while capable of providing assistance in wide ranges of walking speed. Our system is an autonomous bilateral hip exoskeleton that has 3 key components that makes our system novel. First is custom interface made out of carbon fiber, such as frame structure as well as back plates allows for better conforming to user's body and fits wide ranges of body sizes. Second is a sliding thigh cuff design that mitigates any problems that can be caused from wide ranges of movement, such as excessive hip flexion during stair ascent. Third is a fully housed electronics backpack that allows to control the exoskeleton autonomously, as well as logging users' kinematic information from multiple mechanical sensor data. We can go back to our original control tier diagram, but this time I can expand out below level later. In a conventional way of designing a closed-loop feedback control is using a benchtop setting, where we can fix the output shaft of the actuator with a load cell and generate a chirp signal to better understand the overall torque band of the system. Systematically, we tune the PID gains based on the system identification using an SEA dynamic model, and we understood the plant model experimentally from open-loop system response. And overall, with multiple simulation and experimental tune, we're able to obtain the overall PID gains in closed loop, yielding about 12 Hz bandwidth. Then there's a question of, will this PID based on benchtop setting actually account for dynamic locomotion when integrated with an exoskeleton system? And if so, will it actually maintain high torque tracking performance during these movements? And if it doesn't yield any satisfactory movement, what are the additional information we can induce to the system to further improve this? With that, I developed a hypothesis for this AIM-1 that integrating additional user state information to this SEA will further enhance the overall low-level tracking performance. The underlying rationale for this hypothesis is that exoskeleton is not necessarily directly connected to the user's musculoskeletal structure. There's a lot of orthotic interface effect as well as skin dampening. Second rationale is that we can induce a user state-based V4 gain to our PID output to further improve the overall performance. To test this hypothesis, I recruited 3 able-bodied subjects walking at 3 different walking conditions. The first is modulating different system magnitudes. The second is varying different walking speeds. And third is asking the subject to navigate through different locomotion modes, such as stairs and ramps. And during these conditions, I compared 2 different controllers. One is using PID based on our benchtop setting results, and the second is using PID plus user state-based V4 gains. So I want to give you a context of how our device is running in real time. So on the left is zero impedance mode. So basically where we're controlling the device in a transparency mode such that the device does not impede the user's movement. Right is we're providing about 10 Newton meters of a system magnitude on the hip flexion and extension. You can clearly see that there's a lot of actuator movement because of the overall human exoskeleton system that has somewhat of a flexibility. And this tracking performance we can plot in time series graph, and you can clearly see that on the right graph where the orange curve doesn't yield a nice tracking performance. So we can plot the same time series graph as a root mean square error over a given gait cycle across all the conditions. Plotting this result in RMSE, we can observe that there is a trend at least for the system magnitude as well as walking speed in terms of torque tracking performance. We can fit a second order polynomial curve to these conditions and expand a similar proportionality to locomotion modes. And using this feed-forward function, we can obtain the finalized function as a function of the system magnitude, walking speed, and locomotion modes. And using this, we ask the subject to go back to our original testing conditions, and this, using feed-forward gain, we're able to reduce the overall tracking error by up to 20% across all modes and conditions. So we can plot this usage of feed for on the same time series graph that was shown previously, and we can clearly see that using a user state-based feed for gain, we can further reduce the additional tracking error as shown with the bottom graph. We can look into closely at the bottom negative region, which relates to hip flexion movement, where a greater speed demand is occurred on the SCA, but our feed for gain is able to compensate that. And the person might ask about, why don't you just apply high feed for gain across all conditions? But one of the problems with this was that it can potentially induce some instability in certain scenarios. Some of the discussion points from AIM 1 is that first, the overall feed for gain was able to mitigate the torque tracking error of an SCA. However, there were some assistant conditions such as high assistant magnitude that still showed residual RMSE up to about 2.5 Newton meter. As shown in time series, the tracking error was varied in different parts of the gait cycle, such as hip flexion or extension. So a potential solution to this is maybe applying a different gains based on the user's gait phase information. We originally wanted to investigate the effect of walking speed because greater walking speed leads to greater angular velocity demand at the SCA, leading to overall torque tracking delay. However, there was an inverse relationship that actually plateaued at fast walking speed. And walking speed is correlated with the user stride frequency, so this potentially means that there is a user stride frequency convergence after certain walking speed, hence leading to less changes in the torque tracking error. And this is something that we want to further investigate in future study. And lastly, we realized that more feed for gain is not necessarily better. For example, during zero impedance mode, if we induce high feed for gain, we change the overall PID performance to be a bang-bang control, which leads to overall instability. So this leads to an idea that indeed, overall inducing additional user state variable into even a low-level control can further improve the overall performance of an SCA. With that, now I would like to move over to AIM 2, user state estimation. One of the key aspects of using an exoskeleton system is that the person does not necessarily just experience level ground locomotion during daily activities. Rather, the person experiences multimodal locomotion, such as going up the ramp or coming down the stair. And typically, we like to classify the common daily locomotor tasks into 5 modes: level ground, ramp ascent and descent, and stair ascent and descent. If you visualize the underlying joint biomechanics for these modes, we can clearly see that the biological joint demand is different across modes. And this indicates that the assistant paradigm using an exoskeleton system, such as the system magnitude, should be different across modes. And additionally, the different timing of the biological joint movement indicates that there is a user gait-based information is an important state variable to provide accurate assistance. I want to explain about what gait phase is, and before that, I want to explain what gait cycle is. So gait cycle represents the user's limb movement during locomotion. And because there's a cyclical nature of locomotion, we can represent this as a repeating phase variable by setting a defined gait event as 0%, such as heel contact or toe off. And this is an important user state variable because it has a direct correlation to the exoskeleton assistant timing. And this phase variable is time independent, allowing for accurate assistance to be provided at a desired location of the gait cycle. This time we can go back to our 3-tier control approach, but I want to expand out the high-level layer. So you can imagine if the person is wearing an exoskeleton system, and during walking, there's going to be different sensory information that's going to be logged from the onboard mechanical sensors on the device. And using this data, we can feed into our relevant user state estimator. In my case, we utilize a different machine learning approach. And the output of the user state information will be brought down into mid-level layer, where we can generate relevant hip flexion or extension joint torques. So this really showcases that for user state information, mainly locomotion mode and gait phase, which has direct correlation to a system magnitude and a system timing, we can specify the joint torque at the mid-level layer. What are the common literature practice that has been done in the field? First, locomotion mode classification. A common method is using sensor fusion approach using different wearable sensors, integrating with the machine learning algorithms. One of the key limitations of this approach is that often this method requires additional sensors to be worn outside of exoskeleton sensor suite, which can be cumbersome. Second limitation is that translating this model to a novel user is limited because often these models are tuned on a user-specific basis. Second is gate phase estimation. A typical way that's been practiced in the field is using an event marker on the user's heel, such as foot switch, and linearly interpolating the time since the recent heel contact divided by the average stride duration from previous number of gait cycles. This method works fairly well on a treadmill setting at a constant walking speed, but it fails as soon as it tries to move over to an overground situation where the overall estimation is delayed during mode transition, leading to an exoskeleton system being lagged. Another limitation is that it's not robust to other locomotion modes such as stairs where a person can easily miss heel contact. I want to explain about how we would implement a machine learning approach to control these exoskeletons and estimate relevant user state information. First, you'll ask the subject to navigate through different terrains, and this approach can be applicable to not just mode classification, but also gait phase information. And during walking, there's going to be different kinematic information based on such as encoder or inertial measurement unit on the device that tells you about how the user is moving in space. And we can extract out additional features from these raw sensor signals with a defined window size using a time domain feature such as min-max, mean, standard deviation, or recent value. And using this full feature set, we can integrate or implement into relevant machine learning algorithms to output or classify or regress the current times user state variable. But there are definitely key limitations of current literature methods. First is often these models are discrete in classification, such as classifying the locomotion mode once or twice per gait cycle. Another limitation is often these models are subject dependent, requiring additional user-specific tuning. And lastly, most of these studies do not really evaluate the model performance in realistic scenarios, such as will it work well in unseen terrain context. With that, I developed a hypothesis for this AIM2 that leveraging deep neural network approach for classifying and regressing the user state information will enable multimodal locomotion for powering exoskeletons. My underlying rationale for this hypothesis is that deep neural nets leverage an end-to-end approach where we can integrate the feature extraction state as part of training process, allowing for further extracting a relevant representation of the raw signal. To test this hypothesis, I first investigated locomotion mode classification. I utilized an open source biomechanics data set that was collected from our group, including different wearable sensors that relate to hip exoskeleton applications, such as trunk and thigh inertial measurement unit, as well as hip encoders. 20 subjects navigated through the simulated terrain park consisting of different ramps and stairs and level ground that can be height adjusted to be different inclines and stair heights. Using this data, I was able to develop a convolution neural network-based classifier where our classifier is novel in two parts. One is that it's subject independent, so it can be used to a novel user. And second is that it can continuously classify the user's locomotion mode in real time. Our CNN-based approach was able to reliably classify the user's locomotion mode across all conditions with about 3% classification error when fully optimized. This is beating all the benchmark machine learning approach that's commonly practiced in the field by about 60%. And as you can see, for some of these benchmarks, the overall error performance converts to a similar rate. And this is an inherent limitations of using manual feature extraction, whereas CNN model is able to include this as part of training process. One of the key evaluations that we wanted to do during this study is to understand the generalizability of our model performance to unseen terrain conditions, such as will it work on other stair heights. This is an important analysis because it validates the model performance in realistic scenarios. Overall, our model performed reliably with only increasing 3% error during this lead one setting validation. This analysis can be expanded to interpolation and extrapolation region. Interpolation is testing on a train setting that is within the range of training data set and vice versa for extrapolation region. Overall, interpolation region only increased about 1.2%, whereas extrapolation region increased about 5%. One thing to note is that our data set included the full ADA building accessibility guidelines capturing all possible ramp inclines and stair heights. So we expect that our finalized model can have a reliable performance in a conventional scenario. And then we wanted to test our hypothesis for gait phase estimation. Our previous study on mode classification was an offline study, so we also wanted to validate the feasibility of real-time inference. We utilized a robotic hip exoskeleton, including similar sensor suite as our previous study, such as joint encoder and inertial measurement unit. 10 subjects navigated through the same train park, including ramps, stairs, and level ground. During walking, we utilized a biological torque controller where we generated a joint torque trajectory that is relevant for each given mode. And using this data, we trained a single unified convolution neural network model that can work well across all 5 ambulation modes. So you can kind of think of it as subject, whether the subject's on stairs, ramps, or level ground, a single model can output the current times user's gait phase information. We wanted to compare our performance relative to what's commonly practiced in the field, such as the analytical method that I previously explained. On the top is the gait phase estimation using the baseline method, and the bottom is the relevant joint torque trajectory using this phase estimate across all modes and mode transition. You can clearly see that with the red line that there's a lot of discontinuity and poor performance using this baseline approach. Conversely, using our CNN approach, you're able to reliably estimate the user's gait phase as well as relevant joint torque trajectory across all modes and transition, yielding about 5% root mean square error across all conditions. This is about 69% better than the benchmark when we're talking about the actual generator system profile to the user. Another important thing is that we yielded about 67% reduction in the phase estimation RMSE during mode transition, so we can really reliably provide a smooth torque trajectory during these mode transitions. We wanted to see the feasibility of expanding our same control approach to other user state variables as well as other exoskeleton applications. So first is that we utilized a robotic knee exoskeleton and estimating the user's ground slope in real time. And indeed, we were able to use the same approach. We can also expand it to estimate the user's walking speed using a powered exoskeleton. And we can even further expand our approach to estimate internal user state variables, such as estimating the user's biological hip joint movement during locomotion. One of the things that we've learned through this AIM-2 was that the importance of leveraging user-specific data. So these bar graphs indicate the amount of data used to develop a gait phase estimator, except for the red one, which indicates the baseline method. So there's user-independent, user-dependent, and there's semi-dependent. So the semi-dependent model is utilizing a small amount of additional user-specific data on top of user-independent model. And our semi-dependent model was able to further improve the baseline model performance, especially during dynamic movement. This was mainly possible because the model was able to fine-tune the baseline weights to understand the user-specific gait dynamics. This is an exciting result and opens the door for potential application in clinical population where a large amount of data collection is cumbersome, such as generating a user-independent gait phase estimator for stroke subject. We wanted to see how we can implement this leveraging user-specific data to our system. So we developed an idea of an online adaptation of gait phase estimation. So after my gait phase estimation study that I previously presented, we've actually developed a user-independent gait phase estimator that works well for able body, yielding about 7% RMSE to a novel user. So imagine a person is wearing an exoskeleton system, and during walking, we can modulate different train contexts, and this can be different walking speed or different locomotion modes. And in real time, the device is going to start generating a sensor signal that is relevant to the user's specific gait patterns. And using this data in real time, we can further adapt the baseline model to learn the gait dynamics of a novel user and further improve the overall performance. We wanted to validate the feasibility of implementing online adaptation to a novel user. So I recruited one subject to ask them to walk on a split belt treadmill, setting in 2 different walking speeds. The reason was to mimic the asymmetric gait pattern commonly exhibited from clinical population. So the treadmill was set at 0.8 and 1.2 meters per second. I've implemented a user-independent model, phase estimation model, and after about 30 seconds, which is about 6 iterations of total adaptation, we're able to further adapt the baseline model to learn the novel user's gait dynamics. This was about 63% reduction in the overall phase estimation RMSE when using this online adaptation paradigm. And this is an exciting promise because it opens the door of implementing our deep learning approach to a potentially clinical population by integrating this Omer adaptation strategy. So some of the discussion points for AIM-2 was that we were able to develop a deep learning-based approach to robustly classify and regress the user state variable. And this was possible because CNN has an end-to-end approach of integrating the feature extraction state as part of a training process. Second, we were able to validate the feasibility of real-time inference as well as generating a reliable assistant profile using our system. And lastly, we learned that there's an importance of utilizing user-specific data, which can fine-tune the baseline model to further understand novel users' gait dynamics through an online adaptation. With that, I would like to move to my AIM-3, which is translating this technology to clinical population. Stroke is one of the leading disabilities with large size in population, with a case of about 900,000 annual cases in the US. The majority of the stroke survivors experience hemiplegic gait after recovery, leading to an overall reduced overall gait quality. This asymmetric gait is caused due to the weakness in the distal area muscle coordination and resulting in a compensatory movement at the proximal hip joint. And this inefficient gait pattern leads to 1, greater energetic demand, 2nd, reducing the walking speed, 3rd, lowering the overall community ambulatory capability, leading to overall reducing the quality of life for these patients. So there's definitely a great need of utilizing exoskeleton interventions to this field. First, researchers started to tackle this problem when using an ankle exoskeleton system because there's a weakness in the distal area. Different researchers such as Takahashi et al. Or Awad et al. Have shown decent improvement in improving stroke gait, but the study results vary. And this is because there's a fundamental limitation of using an ankle exoskeleton system for stroke gait. Takahashi et al. Explains this with a concept of APGRF, the anterior posterior ground reaction force. So during walking, the anterior ground reaction force, AGRF, has some correlation with the the subject's body center of mass propulsion in the forward direction. So you can expect that greater AGRF typically leads to faster walking speed. But because the subject cannot really leverage the ankle exoskeleton system to a greater advantage, typically exoskeleton system led to a vertical ground reaction force. So it couldn't really leverage to increase the walking speed. This led to an idea that potentially we can leverage hip exoskeleton to improve stroke gait, because we can induce hip extension assistance for better posture during push-up phase for increasing AGRF. Several literature studies have investigated the efficacy of using a hip exoskeleton to improve stroke gait. Studies such as Gregory et al. Or Lee et al. Have investigated the effect of this compared to the subject's baseline self-selected walking speed as well as spatial temporal gait parameter after weeks of gait training. These few studies show a potential promise in using hip exoskeleton for stroke gait, but there's a limitation. The fundamental problem is that there's a limited information about exoskeleton assistance strategy and its immediate effect on stroke gait. So it was more focusing on the rehabilitation effect of using this device. Additionally, bilateral hip assistance strategies that these devices were using are often based on the able-bodied humans, which is an assumption that two populations exhibit similar gait patterns. So we're starting noticing there's a lot of limitation in the current field. First is that most of these studies are often focusing on the rehabilitation effect and has lack of knowledge in the immediate effect of using an exoskeleton assistance. Second, in the case of bilateral hip assistance, most of the control framework are optimized based on able-bodied humans. But most importantly, there is limited analysis in understanding the biomechanical effect of exoskeleton assistance on stroke gait. With that, I developed my hypothesis for AIM-3 that bilateral hip assistance using an exoskeleton system will improve the stroke subject's gait functionality, leading to an increase in self-selected walking speed. The underlying rationale for this hypothesis is that there's going to be increase of AGRF with greater hip extension assistance. Another rationale is that by providing a system bilaterally, we can further improve the subject's spatial temporal gait parameter, such as providing assistance on paretic and non-paretic side. So how do we actually apply bilateral assistance strategy using a hip exoskeleton? Different assistance strategies have been introduced in the literature for stroke gait. Most common one is the impedance controller, where we can modulate the virtual stiffness and damping to shape the overall joint torque trajectory. But there are some limitations of using this control framework because the profile is varied because it has dependency on the user's kinematic input. Because we wanted to observe the immediate effect of an assistant magnitude, we wanted a more deterministic assistant profile. So with that, we can go back to our original control tier diagram, but this time I can expand out the mid-level layer. In the mid-level control tier diagram, I've implemented a biological torque controller, similar to the ones that has been used in my previous studies. The benefit of using this controller is that I have a full control over the assistant timing and magnitude. And in terms of timing, we set the initial starting point based on the literature studies that have shown good results on able bodies, but we further tune the timing such as onset timing as well as peak timing per subject basis. So overall, we're able to generate a deterministic assistant profile bilaterally during the gait cycle. To test this hypothesis, I set up an experiment by recruiting 5 participants with chronic stroke. So first, subject came in and acclimated to the device and familiarized with the device. And after, we asked the subject to take a baseline condition by asking the subject to walk on an overground 6-meter walkway. And taking the 80% of the self-selected walking speed over ground, we asked the subject to walk on a treadmill. And after we collect the baseline condition, we started the initial parameter tuning, which mainly associated with the system timing. So when subjects were wearing an exoskeleton system, we had an on-site clinician as well as subjects' verbal feedback to fine-tune the assistant timing at a desired location. And after the tuning procedure, we provided 16 randomized assistant conditions ranging from 0 to 6 Newton-meter bilaterally. So after the subject walked on a treadmill for 1 minute, immediately subject walked on an overground walkway to evaluate the overall performance on the subject's self-selected walking speed. Our primary outcome measure for the study was user self-selected walking speed as well as step length asymmetry, because asymmetry has a direct correlation with the overall gait quality. Overall, our exoskeleton was able to significantly increase the user's self-selected walking speed. Indeed, our hypothesis was accepted that bilateral system was an effective assistance strategy compared to the unilateral assistance. Bilateral assistance increased about 15%, whereas unilateral increased about 9% of the subject's self-selected walking speed compared to the baseline of not wearing the exoskeleton system. We can expand the assistance strategy to a detailed assistant condition, and 10 out of 16 assistant conditions increase the subject's self-selected walking speed greater than the MCID, the minimal clinically important difference of 0.1 meters per second. And this indicates our hip exoskeleton can make a clinically meaningful impact. And this is an exciting result because just to give you a better context, that some subjects from our pool were categorized as a limited community ambulator. So by using our exoskeleton intervention, we're able to push them to be in a regular community ambulator, providing them more independence in their life. Another outcome measure that we wanted to look into was an asymmetric index, ASI, which correlates with the subject's gait quality. But overall, there was no statistical difference between the assistant condition on the subject's ASI. But this was not because our system was ineffective, but because we were able to increase the subject's step length bilaterally. So bilateral assistance strategy increased about 9%, whereas unilateral increased about 7% of the subject's ASI step length compared to the baseline. This means that we can induce assistance and change in the user's spatial temporal gait parameter using our exoskeleton system. Bilateral system further increased the user's step length, supporting the argument of a greater increase in the self-selected walking speed using bilateral assistance. However, further investigation may be needed to fully optimize the ratio between the paretic and non-paretic side to fully optimize the assistance such that not only we increase the subject's self-selected walking speed, but also improve the subject's ASI. Another aspect that we wanted to kind of investigate was the effect of exo assistance on the user's HRF. We used the concept of paretic propulsion. This is a nice variable because it integrates both not just the HRF, but also the subject's asymmetry. The way to calculate is that we take the integration in the time domain and compare the ratio between the paretic side and the non-paretic side. While there was some improvement in the overall paretic propulsion, the results indicated that the system there's no statistical difference between the assistant condition on the subject's paretic propulsion. And this may be due to maybe low subject number, but also may be due to there's an offsetted assistant timing that maybe the exoskeleton assistant was not in line with the user's biological joint moment. Some of the discussion points from AIM 3 was that first, bilateral hip assistant was able to increase the subject's self-selected walking speed. And this was possible because there was a greater hip extension led to better ankle push-up. However, we didn't see any improvement in terms of subject's step length asymmetry, but this was not because the system was ineffective, but it was rather because we increased the subject's both paradic and non-paradic size step length. And the future direction from this may be investigating how to optimize the assistant level bilaterally to improve not just the ASI, not just the walking speed, but also ASI. And lastly, our hip assistant strategy did not have any significant changes to the subject's age or F, and this may be potentially due to the offsetted and the assistant timing. So this overall pilot study was to understand the effectiveness of hip assistant to improve stroke gait. One of the future directions from this study that we're really excited about is optimizing assistant timing. And perhaps with more advanced methods such as human-in-the-loop optimization, maybe we can have a better assistant timing optimization rather than a qualitative method. And this can potentially further improve the overall performance of using an exoskeleton to improve stroke gait. With that, I would like to make a few closing remarks. In summary of my research aims, at first, I was able to optimize an exoskeleton design for maximizing human exoskeleton performance. Second, I was able to implement an adaptive control approach based on user state estimation for these exoskeleton controls. And third, I was able to translate exoskeleton technology to improve gait functions of a stroke patient. With these research aims, during my course of PhD works, I was able to make a number of research publications. My research made several meaningful contributions to the field. The first is that I was able to completely understand how to design an exoskeleton system for better human outcome measures. Second, I was able to advance the exoskeleton control framework by integrating real-time user state estimators. Third, I was able to translate an adaptive exoskeleton system strategy for clinical population. But above all, I was able to make positive impact in providing holistic insight for future exoskeleton designers in creating more efficient exoskeleton system. It sure was a long journey over the last 5 years. I've walked with an exoskeleton system for maybe several hundred hours, and there has been countless nights of late night experiments, and I can't really even count how many days I was sleep deprived through this PhD years. But this was all possible because of the friendship that I had through this journey. And to be honest, my research contribution is maybe less than 1% of all the things that I presented today. And all the remaining credit goes to my advisor, my mentor, lab mates, colleagues, and above all, my friends. And I really sincerely thank you all who made all this possible and got me through this. I wanted to acknowledge my committee members, Dr. Aaron Young, my advisor, Dr. Greg Sawicki, Dr. Mazumdar, Dr. Omer, Inan, and Dr. Geza, Kogler. I want to acknowledge my HIP Exoskeleton team members as well as EPIC lab members. These are my funding sources, and now I would like to take questions. Thank you.
Aaron, would it be okay if I ask my question now?
I think we're going to do audience questions first.
Can't hear you, Aaron.
Aaron was saying that he wanted to do an audience question first.
Yeah, sorry, Omer, if it's okay, we're going to do audience questions first, and you'll be. Oh, great, then go ahead.
This would be an audience question. Okay, so I just wanted to say that I've been to a lot of PhD defenses, obviously, right, with my own students, with other students, and I've been on, it's gotta be more than 60 PhD committees that Georgia Tech at least, I've been in other places also, and I have to really congratulate you for doing excellent work, but also taking a
much, Omer. Thank you.
Questions? So who wants to start out?
Feel the same. So I'll go with Omer's comments.
Thank you, Greg.
I guess I'll start. So my question kind of goes with the stroke ambulation. So at one point you kind of mentioned like ratio on assistance. Do you think there would be incentive to like look into creating like asymmetrical assistance, like increasing assistance or decreasing assistance on one leg over the other during? Would that help with decreasing the asymmetry in walking, or is that?
So the challenge of, taking a naive approach of providing more assistance on the phoretic side, and I guess repeating the question is that Reese was asking about how do we further optimize the assist ratio bilaterally for stroke gait. I think that's the question. One of the challenge was that initially we took a naive approach of providing more assistance on the phoretic side and maybe less assistance on the non-phoretic, kind of hoping that it will yield overall better ASI. But we start to realize that it's not just about assistant magnitude. There's a lot of, we have to focus about assistant timing as well. That if the system overall is not congruent with the user's internal biological joint movement, even though we provide high assistant magnitude, we can't really yield better ASI performance. So in my opinion, we need to not just focus on magnitude, but also assistant timing at the same time. So there was some limitation of this pilot study was that we qualitative or subjectively tuned the assistant timing based on the clinician's feedback as well as subject's feedback. So something such as like human in the loop, automating the tuning more of a quantitative outcome measures may be a way to fine tune the assistant paradigm for phoretic and non-phoretic side. So
Thank you.
I'll go. Yeah, awesome job, Inseung. That's a lot of work. My question was about your like gate phase estimation and locomotion mode classifier part of your work. So you said initially in your talk that your motivation was to build all these tools so that you can eventually take all this outside the lab, right? And the two things that come to mind for me that are different from what you've done to what would be outside the lab is, one is you've obviously covered a lot of ground with all the tasks that you've trained your thing for, but there's obviously going to be tasks that potentially you haven't trained for, like let's say turning or standing or jumping or whatever, right? So I was wondering, just philosophically or even in terms of your own controller, if you're doing tasks that aren't in the actual labels that you've trained it with, will these kinds of classifiers misclassify this other task into one of those tasks? Or will it just be like, okay, that's something that I've not seen, so I'm just going to ignore it and do nothing?
So yeah, I think the question that Laksh was asking about is like when you're actually translating my control approach that was presented in A2, mainly the gate phase estimation, or maybe mode classification too, when we try to translate this to the real world, we're basically classifying this into 5 ambulation mode that is commonly exhibited from daily locomotor tasks, but there's far many different activities and how you would do during daily movements, or even gate phase, for example, which I do acknowledge the limitation because if you think about other non-cyclical tasks, so this gate phase has some sort of baseline assumption that the movement will be cyclical. So in a case of non-cyclical tasks, it may be limited. And in my personal opinion, that eventually to be actually used in a real world case, that it has to be a hybrid system. So it's not just about purely based on gate phase estimation, but I think one of the exciting directions that we want to take is using a biological hip joint moment estimation where we can really directly estimate the underlying joint kinetics. So this is the work with my colleague Dean Molinaro, where we can just literally understand how the human is moving in space, like whether that's not just locomotion, but maybe standing, sitting, or turning, and so forth. So if we directly control using an exoskeleton system with this paradigm, along with maybe gate phase estimation, in the context of locomotion where we're commonly experience like 5 ambulation mode, such as a hybrid system, may be the final solution.
thanks. Yeah, that definitely would like solve the problem, I think. Thanks. Can I ask a quick follow-up?
Yeah, of course.
In your experience of, you said you've walked with it yourself hundreds of hours and you've done all these experiments. Does adaptation play a role in how well your classifiers are able to classify over time? Like I know initially when you were at Exoskeleton, you walk with it in a certain way, but then, you know, from your research, probably research from Stanford, we know over long times there's some adaptation that happens in the kinematics of how we move. So do your classifiers kind of get worse over time, or do they learn to learn or something like that?
So Laksh was asking about adaptation paradigm aspect of using an exoskeleton to an expert user versus novel user to these mode classifier or maybe gate phase estimator. In my opinion, there's definitely limitations of using this machine learning or deep learning approach when you're developing a user independent model, because it has an inherent assumption that the kinematic patterns, because we're using basically mechanical sensors on the device to map to relevant modes or phase estimation. So if the joint kinematic patterns of a novel user experience completely different paradigms, the way that the person walks, it will, to be honest, it will not be as robust as what you will see today. And this is why we're really excited about on the adaptation paradigm, where the model starts to learn the user-specific gait patterns to further optimize the performance. This paradigm was originally generated because of when we're trying to implement the gait phase estimator to a stroke patient. There was a lot of inter-subject even variations of gait patterns across subjects. So it indicates that it's really hard to generalize the overall gait patterns in a clinical population. So it makes more sense to start off with a stock controller, but eventually adapt the model in a matter of minutes to the novel user, so we can develop a better gait phase estimator. So
That's awesome. Thanks.
cool. Yes.
Since you already, that's like, I have a question regarding the adaptation from the machine learning approach, and how do you balance the pre-trained model weights versus what it's learning? What's the balance of old data and new data that is coming when training?
So that's an excellent question. Jonathan asked about how do we balance the new data set that's being streamed to this online adaptation when you're learning compared to the initial weights that the model was learning. So Dean, my colleague, and I were playing around with these multiple different learning rates and stuff. There is definitely fundamental limitations of doing this approach, which can cause what we like to call a catastrophic learning or failure, because the new models may have learned or overfit to the new user. So a potential way to mitigate this is maybe we can have, we can lower the overall learning rate or tune the learning rate, or maybe have different models so that whenever we're at, let's say subject's going on the stair, we don't want the model to overfit to stair. So maybe we need to have different number of models that can be trained such that we don't forget the level ground. Or maybe if you're training the most recent locomotion mode for a long time, we don't update the model weights. Or maybe we can have a threshold that if it's yielding certain RMSE that we don't train. So there can be a number of different ways to kind of mitigate this problem. But yeah, that is something that we're definitely looking into. Cool. Yes.
So in your exo design slide, 1, 2, 3 with specs, it's like 1 and 2 versus 3. You know, with B3 you have increase peak walking speed, increase peak, torque, and it's lighter weight. So is that a result of like just increased torque density motors available on the market, or did you find a lot, through your iterations of design, did you find kind of ways to improve the system to kind of optimize for bang for your buck exoskeletons?
Right. So there are multiple, I guess, additional design concepts that went to this final iteration. To be honest, the first two iterations, I chose a ball screw driven actuator. In terms of gear train, it was mainly because it was way cheaper, to be honest, than the harmonic drive, which is fairly expensive. But the better answer for this was that we had to really minimize the gear ratio. The gear ratio is the critical part because that overloads the entire SEA performance. So the first two were has about 100 to 200 to 1 gear ratio, so it's fairly high. It's basically giving an overload to the SCA system, whereas our system is about 50 to 1. So at the end of the day, the gear transmissions that are available in the field is pretty much there. There's no new mechanism that's going to happen in the next whatever years. So we had to choose not the weight of the gear transmission, but the gear transmission that is has low gear ratio. And then we could sacrifice the overall weight, because that has the overall weight of the exoskeletal system, the direct relevance to the human output measures. So we really had to cut out the weights of the system. And it's funny because a lot of times researchers focus on developing a really lightweight actuators by reducing 100 grams. But at the end of the day, you focus on developing putting an orthotic interface that's off the shelf that increases about 1 kilogram, for example. So then overall, when you think about it, exoskeleton system is not just about actuators. So that's why we start investigating, working with our on-site clinicians and orthotists to really develop the next generation orthotic interface, so where we can really lose or reduce the overall weight from there, but still maintain the actual performance at a desired spec. So.
Owen has a question online.
Yes. Owen, yeah, Owen. So your question was, does the subject, stroke subject, walk at different walking speed for the paretic and non-paretic side? That I am not exactly sure, because I haven't looked into the actual, the stride length and the stride frequency to calculate because we've used the overground walkway to just figure out the average walking speed over a given distance. But we can calculate, we're using the stride length and stride frequency to look into the individual ones. Because there's an assumption that the walking speed is constant, so you're trying to, the increase of propulsion means the increase of braking force. So the initial one. I haven't really thought about that in terms of braking force, but I guess it makes sense because you're saying that the constant walking speed, you'll have like equal amount of negative plus positive in terms of ground reaction force. So yeah, but I to be honest, I haven't thought about that in regards to the first part of the graph. Yeah, something I can definitely say. Yeah. Yeah.
Okay, there's a question in the chat. So it says, I might have missed during the presentation, how many DOF does this EXO have, and how many of them are powered, and also is there any mechanism for misalignment between the EXO axis and the human axis?
So the question is, was the question about the exoskeleton system that I've designed, or is it? Okay, so the system is one DOF. So we provide a system the sagittal plane in the flexion extension direction. It does have additional degree of freedom in the passive joint for allowing for abduction and adduction, but it's purely passive. There is currently no mechanism as to mitigate any misalignment, or I guess during real-time control, there's no way to adjust the misalignment between the exo axis and the human axis. So we try to ensure that the better fit is done with the device when we wear the exo, such that the biological joint moment, a joint axis is in line with the system axis. I don't know if that answers your question. So, there was another question. Yes.
Nice job, Vincent. I know that you have built multiple versions of hip exoskeleton 1, 2, 3. Let's say you get to build and think about a design of V4. What would you like to build? I know that there are multiple specs that you need to consider. You know, it doesn't have to be a specific application, but do you have any thought on V4? Let's say you get to design one.
So some of you guys might know, but I'm staying here until December to finish up some of my work. And one thing that I'm really excited about potentially is developing a hip knee exoskeleton. And the reason is when we are working with stroke patients during stair ascent mode, there's some limitations of using just hip exoskeleton for stair ascent. And that is mainly because of the foot clearance during stair ascent that we really need maybe knee exoskeleton to compensate that. So something that I might do as a side project while I'm here is maybe developing a hip knee exoskeleton for a stroke gait. So this is something that maybe if I have time, the next version 4 exoskeleton will be integrating additional knee exoskeleton system. So. Yes, Jenny.
Last question.
Yeah, I just have one kind of broad question for you to probe a little bit of kind of what you learned over the course of your 5 years here. So I think one of the things that is a huge challenge that maybe you didn't dwell on at all during the presentation is taking able-bodied research and translating that into a clinical population. So when you were kind of doing that and taking able-bodied studies into the stroke population, or just for any clinical populations you can imagine working with, what portions of the process would you recommend that people kind of consider sooner? Was it maybe mechanical design, things that could have been tweaked to better fit? Is it control approaches? Did it come in machine learning and gait phase estimation? What kind of advice would you give in recommending what people look at sooner, kind of keep in the back of their mind during the process?
So Jenny asked about what are some of the things that is important when you're translating able-bodied human study results to clinical population. My past 5 years experience working with stroke patients is that you don't really just focus about human outcome measures or torque tracking performance or perfect exoskeleton design when you're working in clinical population. Even if we say our error is what number of error using gait phase estimator, and if it doesn't really provide nice assistance that the subject is content with, then the subject will not walk faster or not want to use it. So at the end of the day, we're developing an exoskeleton system that these patients want to use at their house, right? So there's a lot of things that I think researchers kind of miss is that we have a classification there, and this may be contradicting my work, but we care so much about the accuracy on offline studies and stuff, but really neglect the importance of human outcome measures, such as whether the subject is so there's a lot of additional qualitative subject feedbacks and stuff that is really important. That we really need to not utilize a naive approach of this worked well in able-bodied humans and reducing whatever metabolic cost, it should work well in stroke subject. I think we should focus on rather just developing a control framework or hardware that is directly related to a clinical population. And you cannot generalize stroke gait. So another key limitation is that we were trying to develop something that works well for everyone. And even able-bodied humans, there's a lot of intersubject variations. And if you think about clinical populations, it's the gait deficiency due to stroke. So it's not the fact that you're generalizing stroke gait I think is somewhat limited too. So that's some of the things I guess. anecdotally I'm speaking from my past experiences.
Okay, I think with that, we'll wrap it up. Thank Inseung one last time. Okay, so